Okay, Assalamualaikum and good evening, everyone. Okay, so today our group will going to present SCL on subject MTH3104, which is mathematical method, and we are from group 4. And I am the leader for the group, and my name is Faizatul Shamini binti Nur Ismail, and my metric number is 200333.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Hidayah binti Abdul Jamil. My metric number is 203560.
Hi everyone, my name is Christina Iman Maisara binti Amahir and my metric number is 202433.
Assalamualaikum. Hi, my name is Azidan Aiman bin Hamdan and my metric number is 200297.
Hi and Assalamualaikum. My name is Raihana binti Ismail alias Abdul Malik. My metric number is 200712.
Hi everyone, my name is Nura Ayuni binti Abu Jamil and my matrix number is 203854.
Hi, my name is Muhammad Zakor bin Yusuf and my metric number is 204246.
Right, so we are going to talk about Taylor polynomial approximation. So before we go into detail, we need to know what is the Taylor polynomial is about. Okay, so the Taylor series is a power series for a function around a point, and this Taylor polynomial is good for approximating a function f(x). So here we can see that if the function f is n times differentiable at point x naught, then we can define the nth Taylor polynomial for function f around a point x equal to x naught as given in the slide. So the formula is given in the slide. You can see the formula. So we can compute the Taylor series. We can compute a Taylor series by finding the nth derivative and substitute them into the formula Pnx. Next.
Okay, so for the derivation for Taylor polynomial of order n, so let f be a function with derivatives of order k for k is equal to 1, 2 until n in some interval containing a as an interior point. So then for any integer n from 0 through n, the Taylor polynomial of order n generated by f at some point a is this polynomial here. Okay, so from the Taylor polynomial formula, as we can see in the first term, f a plus f prime a times x minus a is actually the linear approximation. So if I add one more term, which is f double prime a divided by 2 prime times x minus a to the power of 2, actually this is the second order derivative. Okay, and if I continue the process up to order n, which is n factorial equal to n times n minus 1 times n minus 2 until 1. So we will get the whole formula for Taylor polynomial of order n. So for this formula, we can write in a sort of compact form, which is like this: Pn x equal to sum of from 0 until n, f to the power of I times a divided by I prime I factorial times x minus a to the power of I. Okay, next. Okay, so for the Taylor polynomials approximation, okay, a Taylor series about 0 is called a Maclaurin series. A Maclaurin series is therefore a power series in X and has the form like this: summation of from n from 0 until infinity, and f to the power of n times 0 divided by n factorial times x to the power of n equal to f0 plus f prime 0 x plus f double prime 0 divided by 2 factorial times x squared plus until f to the power of n times 0 divided by n factorial times x to the power of n. So this is some example for the Taylor polynomials approximation in Maclaurin series. Okay, that's all.
Okay, so now I will talk about the applications. Okay, next. Okay, so Taylor applications is in physics. Okay, so one of the major use of Taylor series is to approximate complicated function with easy polynomials. And this happens more often in physics. We use physics laws, principles, reasoning to derive equations that will regulate the behavior of the system. But those equations are too complicated to do anything useful with them. So instead, we approximate those equations with Taylor polynomials, and we can draw all kinds of conclusions. So in this presentation, I'm going to present one example of something slightly different where Taylor polynomials also help add light to a physical concept, which is kinetic energy. So the kinetic energy of a particle is the energy it will have because it is moving and has a velocity. If you have taken a physics class, you are probably familiar with a classical formula for kinetic energy. So the kinetic energy is T is equals to 1/2 of the mass times the square of the velocity. So now in the relativity, the formula for the kinetic energy is quite different. So you probably are familiar with Einstein's famous formula that says that the energy of a particle is mc squared, where c is just a constant. It's the speed of light, but that is the total energy of a particle. So the kinetic energy is the energy that has because it's moving. So the total energy minus the energy it has at rest. So now I'm distinguishing between the mass of the at rest, m0 and m. That will be the mass when it's moving at velocity v. So now there is also an equation that allows us to write the mass at an arbitrary velocity in terms of the mass at rest. And when I use it, I get this. The mass is the mass at the rest divided by power of 1 minus v over c squared minus m0 times c to the power of 2. Okay, so okay, next. Okay, so here is the formula for the kinetic energy in the relativity. So v is variable. So I'm going to isolate the essence of the function. The function is -1/2 power of 1 minus the variable. where the variable is v over c squared. So I want to approximate this function with something simpler. So the first Taylor polynomial would be the tangent line. So f0 plus f prime 0 times x, and we can compute those values. So the value of this function at 0 is 1 plus 1 over 2 times x. So the function that I have is 1 over square root of 1 minus x squared. And in this case, the approximation will be 1 plus 1 over 2x squared. So let's go back at the top and use this approximation. So m naught times c squared is simply multiplying. So now the first term is 1, but I have a negative 1, so it's vanished. So the next term is 1 over 2 of the variable squared. So the variable is b over c squared. And then if you group those terms together, it will exactly become 1 over 2 times m naught times b squared. So it's the classical expression for the kinetic energy. So the classical expression is the first non-zero term on the Taylor series expansion of the relativistic expansion. So now I want the second polynomial. Okay, so the second Taylor polynomial, I need to add one more term, which is f double prime 0 over 2 factorial times x squared. So now I will take this function and take the second derivative and evaluate at 0 and divide it by 2. And if you go through the whole process, in this case, the coefficient is 3 over x squared. Or down here for this other function, it will be 3 over 8x to the power of 4. And now at the first equation here, we have to add one new term, and it will be plus 3 over x times v over c to the power of 4. And when I simplify and group everything together, this is the first relativistic correction to the classical expression for kinetic energy. So this is the classical expression for the kinetic energy, and I could keep adding more terms if I need better and better values. Although at some point it may be worth it to use the original expressions. So that's all from me. Thank you.
Next is the second Taylor series application in real life, which is in mechanical engineering. For information, Taylor series is just a mathematical expression utilized to expand a function or writing in some or other simple term so that one can obtain an approximate solution for a particular value when put in the function. So Taylor series will be using in mechanical engineering in real life. For example, there is a Taylor series formula like Iman present before this, and this the example applied to sign act like Rahana present to us before this. So next slide. So now we consider in mechanical engineering situation. So consider a typical SFD, which is a computational fluid dynamic, which is application of Taylor series in mechanical engineering. For this problem, it can be used using software like ANSYS to solve this problem. However, Taylor series also can be used in this problem to solve this problem. So this Taylor series can help this problem to solve this solution by reduced into very simple term like sign act before this, where using different numerical technique, the final solution can be obtained by convergence criteria. So as a result, if a mechanical engineer is present with a problem having complex equation, with no easy way to reach the problem, to reach the solution. So Taylor series can be used to solve these all of the problem that they face. So Taylor series can help them to solve their problem. So this is what the example of problem, another problem that uh, mechanical engineer use Taylor series to solve your problem is like heat and mass transfer problem and inflate dynamic. I think that's all for me. Thank you.
So next, I will explain more about example calculations. Next slide. So the question that we use is find the first three non-zero terms of the Taylor series for function square root of 8x minus x power of 2 about a equal to 4. So Hazidan will explain more about the answer.
Okay, now I will continue to explain about the answer for this question. So the formula is as shown in the slide, which is FA plus F prime A times X minus A plus F double prime A times A minus A power of 2 over 2 factorial plus F third prime A times A minus A power of 3 over 3 factorial. And then it say that A are power of 4, so then we need to substitute A with 4. So next slide. Okay, now I will explain further. As the question shown that function square root fx minus x square. So now we put it as fx minus x square power of 1 over 2 because it's much easier to solve it, to derive it. Okay, first thing first, we substitute the x with 4 and then we solve it, then we get the answer is 4. For the first derivative, we need to derive it using the power rule, and we get the answer 1 over 2 times 8x minus x square power of negative 1 over 2 times x minus 2x. Then we can distribute 1 over 2 to make it simpler. Then we get the 8x minus x square power of negative 1 over 2 times 4 minus x. Then we substitute the x with 4 and we get the answer is 0. Okay, now for the second derivative, we need to use the chain rule, and we got 8x minus x square power of negative 1 over 2 times negative 1 plus negative 1 over 2 times 8x minus x square power of negative 3 power negative 3 over 2 times 8 minus 2x times 4 minus x. Then we can also distribute negative 1 over 2, and we get distribute negative 1 over 2 and we need to factorize this negative 1, and we get negative 8x minus x square power of negative 1 over 2 minus 8x minus x square power of negative 3 over 2 times 4 minus x times 4 minus x. Then we simplify it and we got negative 8x minus x square power of negative 1 over 2 times 8x minus 8x minus x square power of negative 3 over 2 times 4 minus x power of 2. And then we need to factor the negative here. And we get negative 8x minus x square power of negative 3 over 2 bracket 8x minus x square plus 4 minus x power of 2. And then we solve it, we got negative 16 times 8x minus x square power of negative 3 over 2. And then we substitute the x with 4 and we get the answer negative 1 over 4. Next, then for the third derivative, we do the same step. Then we need to derive this, and we get negative 16 times 3 over 2 times 8x minus x square power of negative 5 over 2 times 8 minus 2x. And then we got 48 times 8x minus x square power of negative 5 over 2 times 4 minus x. And we need to substitute the x with the 4 and we got the 0. As the question asks, we need to find the first three term, but for the third term we got the 0, so we need to do another derivative. So next, so we need to do the fourth function. So F4, we got 48 times 8x minus x squared power of negative 5 over 2 times negative 1 plus 48 times negative 5 over 2 times 8x minus x squared power of 3 over 2 times 8 minus 2x times 4 minus x. And then we need to factor the negative 1, and we got the and after that we need to expand this, and we got the negative 48 times 8x minus x squared power of negative 5 over 2 minus 240 times 8x minus x squared power of negative 3 over 2 times 4 minus x power of 2. And then we substitute the x with 4 and we get the answer negative 3 over 64. From this all calculation work, now we can do the general solution. So we got function approximately to 4 minus 1 over 4 times x minus 4 power of 2 over 2 factorial minus 3 over 64 times x minus 4 power of 4 over 4 factorial. So the final answer we got 4 minus 1 over 8 times x minus 4, x minus 4 over power of 2 minus 1 power 1 power over 512 times x minus 4 power of 4. Oh, I think that's all from me. Thank you.
So for the conclusion, the Taylor series is useful because it gives a framework for approximating functions. This allows us to approximate values of functions using only addition, subtraction, multiplication, and division of real numbers. Then, we have probed through the complexity of Taylor series and shown evidence of its extensive and very effective applications. The effectiveness in error determination, function optimization, the effectiveness in error determination, function optimization, definite integral resolution, and limit determination is evidence of the Taylor series being an enormous tool in physical science and also in engineering and computation science, as well as an effective way of representing complicated functions. So, thank you.